Irodov question number 1.123. Two bars of masses m1 and m2 connected by a non-deformed light spring rest on a horizontal plane. The coefficient of friction between the bars and the surface is equal to k. What minimum constant force has to be applied in the horizontal direction to the bar of mass m1 in order to shift the other bar? Okay, so let's draw the diagram first. We have one bar m2 and another bar m1. Okay, these are connected by a non-deformed spring. Okay, and then a force F is applied on bar m1. The coefficient of friction is given as k between these surfaces. So what is the minimum force that needs to be applied so that it moves bar m2? Okay. Let's take a hypothetical situation where we have just started to move m1 but m2 hasn't moved yet. Let's see. So let's say m1, it has moved a little bit, so the spring is elongated a little bit. Okay, and this is m2. So there is still this force acting, and there is an elongation of the spring, let's say by a distance x. This was the original location and now it has elongated here. Okay, so we can think like the mass was originally here, now it has moved by that equal distance. Okay, so when the mass was here, let's say that point was A, now the point where the mass is at point B. Okay, and m2 has not moved yet, it is just about to move. Okay, now let's draw the free body diagram for m1 and m2. Okay, so m1, we have force of gravity, we have a normal reaction, we have this force F, we have some friction, okay, in the opposite direction of motion, and as soon as there is some elongation of the spring, there is this force of the spring, there is this spring force, let's say Fs. Okay, now for m2 we have m2g, we have normal reaction, we have friction force Fr, let's say Fr2, and this is Fr1, and the spring force is acting this side. If it is same spring force, which would be k, which is the spring constant, let's say the spring constant is k, so k times x in this direction. Okay, this is n2. Okay, what is the condition when m2 will start to move? m2 will move, let me write it here, m2 will move when the spring force overcomes the force of friction. So Fs is greater than or equal to the force of friction on 2. Okay, or we can write Kx is greater than equal to the force of friction is K, sorry, okay, you know what? The spring constant, let's just assume that as K dashed. Okay, because the coefficient of friction is given as K. coefficient of friction is k. So let's assume the spring constant as k dashed. Okay, so k dash x is greater than or equal to k n2, which is k m2g. Okay, so that's when it moves. Now let's look at mass m1. Okay, now our aim is to find the minimum f that will allow this to happen. So we have to find some correlation. Okay, so this is what I am thinking. This x is the connection between the movement of m2 and what is happening here. Okay, let's look at this. If we can represent this f force as some function of x, then we can do a connection between this and that. So how can we represent f as some connection of x? What we can do is we can apply between these points A and B, or between these two states when the body was at A and when the body is at B, we can apply work energy theorem. So applying work energy theorem between point A and B. Okay, now think of it this way. Okay, so this is actually point A. This is point A. Now M1 will start moving. M1 starts to move when, so there is no elongation of the spring right now. So when F is greater than equal to the force of friction, there is no spring force because there was no elongation, there was just a force of friction that had started. So that is equals to, let's say, k m1g. Okay, but now as soon as m1 starts to move, there is some elongation. Okay, so then what happens, m1 has got some velocity when it started to move here. F is responsible for some acceleration. Now as soon as it starts to move, the spring gets elongated. There is a spring force acting on the other side. So the effect of F reduces. So the velocity, whatever it gained, it slowly will go to 0. So if I draw a velocity versus x graph of m1, as x increases, velocity is increasing at some point, at some x, the force F and the spring force, they balance each other out. Okay, so that is when the maximum velocity is reached. Okay, and then the spring force takes over. Takes over means it is more than this F. So then there is deceleration and slowly the velocity again comes to 0. Okay, so the initial state, if this was A, this was B, the state. Okay, so when we can apply work energy theorem, because at A velocity is 0, at B also velocity is 0. So between those two states, work done by all the forces is equal to change of kinetic energy, we can write. Now change of kinetic energy between A and B is 0, and let's just look at what is the work done by all the forces. So work done by F, the friction force, and the spring force, right? So work done by F, work done by friction force, and work done by spring force is equal to 0. What is the work done by F? F is a constant force, so F times x. both the direction of displacement and force is in the same direction. What is the work done by the friction force? Friction force is in the opposite direction, and that is equals to K m1g times x. Okay, and what's the work done by the spring force? It will be minus half K dashed x square equals 0. So what we are doing here, we are applying work energy theorem between these two states when the velocity of m1 is 0, when it started and when it stopped. Okay. Okay. So from this we have one solution we can see, which is x equals to 0. That solution we can ignore. Okay. Let's look at the other solution then. So f minus k m1g minus half k dashed x equals 0. Okay. Or we can write f is k m1g plus half k dashed x. Okay. Now we have represented force as a function of this x. Now x will move when k dashed x is greater than equals to k m2g. So we can say that the minimum force, so F to be minimum, we need x to be minimum, and x is minimum when k dashed x min is equals to k m2g. So we can write F min is equals to k m1g plus half. Now k dashed x min is k m2g. Or from here we can arrive at this F min is, if I take kg common, m1 plus m2 by 2. Okay. Okay. So just to go back and understand what happened here, the key is where we apply the work energy theorem. We break down the motion of m1 when it is starting. Due to the effect of F, it is accelerating, but as x grows, the spring force is increasing. See, between these 2 points, let's say this is O, okay. Between A and O, what is happening is the force F is more than, greater than Fs plus Fr1, the spring force plus the friction force. Okay. Now as x is growing, Fs is growing. At V max, when the maximum velocity is reached, F force is exactly equals to the friction force plus the spring force plus the friction force. So at this point, Fs has grown so that Fs plus the friction force exactly matches this F. Now post that, what happens is F is now less than the spring force plus the friction force, because Fs has grown more, so this happens. So at some point, whatever velocity was reached, it will decelerate to 0 at point B. Okay. So hopefully I was able to explain that. If you have any questions, leave some comments and I'll be glad to respond back to you.